Hello everyone. Today we have Nitin of UG2K15. He's currently pursuing a PhD at Purdue University. His interests are in programming language theory and formal verification and whatever. Yeah, today he'll be talking about embedding languages in proof assistance. Yeah.
Hey, what's up, guys? Okay, just to elaborate a little more on that, right now, so my current work involves trying to prove certain meta theoretic properties of like this calculus called dependent object types. It's a type system which hopes to capture all the features of Scala so that we can formally talk about Scala like in terms of the syntax and semantics that we understand. This has been it's been a surprisingly long journey, like proving the meta-theoretic properties of Scala has been very difficult because Scala is a strange language and several standard techniques which are well understood for some reason just don't play well with this calculus. And I think it's been an ongoing effort for about a decade, and they've recently had something which looks like success. I guess 5 years from now, we'll know whether it actually was or whether it was just another false start. There have been several false starts in this. Today, I'm going to be talking about how to embed languages in proof assistance. So, right, this is pretty much what I do at Purdue, like most of the time. Right. So when we talk about just okay, quick thing. So I'm not super familiar with how much context you guys might have with this topic. So please feel free to like interrupt me at any point and ask questions. Okay. Right, let's get started. So we're going to start off with a very simple language, okay, just to demonstrate the basic concepts. This is what we call BNF syntax. It's how we represent like the syntax of languages. So this language is a very simple language. It just has natural numbers, which are just zero and successor of n, and expressions, which are just numbers, addition, and subtraction, okay? And the first embedding that we're going to look at is called a shallow embedding, and it's really straightforward. It's basically just an interpreter. You for each syntactic form, we have a function which translates it into like something which is well understood in the host language. So Coq has its own predefined like addition and subtraction and everything. So this is not a very particularly interesting embedding, but it illustrates the basic concept. So with this, we can we can actually run programs in our language and get results over here. So this is kind of useful because it allows us to steal power from the host language. Okay, I didn't have to write down each rule for like evaluating this individually. I didn't have to reason about anything intermediate. But another problem with this is that I actually cannot reason about any intermediate states of evaluation. Okay. For those who are for those of you who have taken the compilers or the programming languages course, basically in a shallow embedding, there's no abstract syntax tree. Okay. So if we want to be able to reason about intermediate states, then we need to be able to construct an abstract syntax tree. And whenever we construct an abstract syntax tree, you can also say that we have constructed a deep embedding. Okay. Uh, so below over here is our deep embedding for the same language. So a common misconception is that deep and shallow embeddings are like the opposites of each other, but that's just because of poor terminology. In reality, deep embeddings just refer to the fact that you do have an intermediate representation that you can reason about, and but like they don't have to be contradictory. Like for example, over here I've constructed the AST over here, uh, but I've connected our deep embeddings to the previous shallow embeddings in order to help us evaluate any expression in the AST. So I could have alternatively written like actual operational semantics for this language where I say like inductive eval r, okay, which is a type. This would be an in this language is just an expression to an expression. And I could literally define semantics. Like for example, I could say add where eval r, give me Ah, as type. Terribly sorry. Right. Essentially, you get the point. Basically, over here, I could have written each of these rules separately as operational semantics. So I'm just going to write it in non-coq, like something like add n dash to n plus n dash. And the point of this is that if I have each of the rules separately, then I can actually talk about the intermediate steps of evaluation. So as you can see, there are like varying degrees of granularity that you can specify. If you don't care about the intermediate states at all, or like the program structure at all, you could just have a normal shallow embedding. If you do kind of care about the program states, you could have a deep embedding. But if you don't really want to talk about the how each step of evaluation, you only care about how the evaluation finally concludes, then you can just write your evaluator in this form and connect your deep embeddings over here to your shallow embeddings over here. So right, I've done it here where we talk about the same so here we talk a little bit more about deep embeddings and the various design choices that you can make when trying to construct those. So right. So the first way of representing syntax is called we call this extrinsic style. So you define your types over here. So right now we're talking about a language which is basically it's lambda calculus extended with natural numbers and an if statement. The if statement, I expect that it would behave like if 0 is the same thing as if false, and if non-zero is the same thing as if true. And is everyone here familiar with lambda calculus, or should I just quickly run through that? All right, I'm gonna assume familiarity with lambda calculus. I'll talk about it in small details here, but yeah. So in this language, first we define the types of the language. So the types that we have are natural numbers and an arrow type, okay? And arrow types are just the types of functions. So it takes it takes something of the first type and returns something of the second type, okay? And I define some convenient notation for that. So now I can say, for example, check and sure enough, it tells me that n to n is a type. Okay, so we also represent variables as natural numbers. So we're using something known as a nameless representation of variables, this thing called de Bruijn indices. And the reason we use it is because it just makes it really convenient to talk about to talk about functions. If you do not use de Bruijn indices, then you have to get into things like variable shadowing and right. I'm super confused in how much detail I should be talking about these things. So yeah, just tell me to slow down if I should, or if I should explain something in more detail. But de Bruijn indices work in basically the following fashion. So each variable represents each variable is a natural number, and it represents an element in the context at that index. Okay, so here's the lookup function, which takes a context and a variable, and it returns the type given at the variable's position in the context. Okay, so here we do a pattern matching on the context and x there, and we talk about what happens in every case. In the first case, we have a context which starts with t. And if we are trying to look up the variable at position 0, then we just return t. Here, however, in the case where we have a context which starts with t, but we're not looking up the variable at position 0, we're looking up the successor of something, then we just recursively call the same function on itself with the tail of the context and the predecessor of the like variable. And if neither of these two cases hold, the other two cases are when you have an empty context, but the variable is greater than 0, in which case the variable is out of scope. And the second case is where you have like, no, that's the only case. Basically the case where the context is empty. Basically you can't look up from an empty context, which makes sense. So this is a very convenient way of representing variables in like lambda calculus. And the reason for this is because in standard lambda calculus, like let's assume that I have a function like this, lambda x, okay? And another function like this, lambda y. Now, both these functions behave the same way. They're both the identity function, okay? But they are syntactically different. And if we represent the variables like using identifiers like we do over here, it becomes quite painful to identify which two expressions are equivalent in some sense. By the way, these two functions are called alpha equivalent, and I'm not going to go into that in detail, but basically when we have names, this identifying whether two functions are actually the same thing becomes like annoying and just another detail that we have to deal with. So instead we just skip over that and we just say lambda 0 to represent the like innermost bound variable over here. And because like variables no longer have names and we're representing them by indices, both of these are just unified into a single concept, which makes our life a lot easier in representation. You will find de Bruijn indices used quite frequently in like in representations of variables in several calculi, like especially another common representation is de Bruijn levels. So de Bruijn indices, they kind of start from the top, de Bruijn levels start from the bottom, and like there are various advantages and disadvantages to these approaches, which we can go over in detail, but I'm not going to cover it right now. Right. So so now we have like types, which are natural numbers and function types. We have variables as de Bruijn indices, and we have our context, which is simply just a list of types. Okay, so so once we have all these components, we can now define our expressions. So these are the valid syntactic expressions in our language. We have variables, lambda abstractions, application, numbers, and if statements. So variables just take a variable and lift them to the expression level. Lambdas, since we're using de Bruijn indices, we only need to pass the body of the lambda. And in doing so, we define a function. And application is just function application. So this is your function, this is your argument, and it returns something. Numbers are just numbers, like naturals, and if statements takes a condition, which is a natural number, the true block and the false block. And yeah, returns an expression. So, and here I just define some convenient notation for like variables. I don't like using var all the time, so I just use hash, and I define application in like using the dollar symbol. So, right, so now we have enough machinery to talk about the syntax of our types and our expressions, as well as something for the variables and context. So with all these things, we can like write a bunch of variables, okay? Like we can actually check if a few things, if we can define certain syntax in our language. For example, we could do lam $0, that same identity function, which I was referring to above here. A little scoping issue. Yeah. And certainly Coq informs us that this is a valid syntactic expression. However, we don't really have any type checking rules set in place, which is why I can also do weird things like this, which just doesn't make any sense because the variable at position 1 is not in scope over here. So this Coq permits it because, well, we haven't taught Coq how to reject ill-typed expressions in this language. So let's just define our typing rules, and that's what we do over here. So like let's run through the rules one by one just to make sure that like they make sense. So the first rule for variables basically just says that if you look up a context G for a variable X and it returns T, then that variable has type T, which makes sense. And like similarly for lambda expressions, we say that if the body of the function is which is E over here is typed as T2 under a context which is extended with the argument, then we can then we can show that this lambda abstraction is typed as T1 to T2. So is this typing rule clear to the audience? Just to quick question, like how interactive are these things normally? Like anyone?
I think this is roughly the level of interaction you generally got.
Right. So if there is silence, should I assume that everyone is mind-fucked, or should I assume that everyone has understood?
If there's silence, you
Understood.
assume understanding and move on.
All right, cool. So so this is the rule for lambda abstractions. So I hope that this rule gives perspective to those who are not familiar with lambda calculus. I hope this rule gives perspective as to why we need the context. So the context basically just contains a list of bindings, like the variable at position 1 is typed by the variable at position 0 has the same type as the type at position 0 in the context. And whenever you enter the body of a function in order to type check it, you need to add its argument to the context so that you can use the argument for type checking, which is what we're doing over here. So like here we are assuming that tlam is a function which is taking an argument of type T1 and returning something of type T2. So in order for this to be true, that means that the body given like the argument in the context is typed as T2. So I hope that's clear to everyone. And right, so given that this is the rule for constructing lambda abstractions or functions, we can use, here's the rule for application. So application says that if you have an expression E1, which is basically a function from T to T dash, and you have another expression E2, which is of type T, then you can pass E2 as an argument to E1. And this gives you a valid expression, which is of type T dash. Basically, if you call the function with an argument of the correct type, it'll give you something of the return type. All numbers are just automatically assumed to be natural, like natural numbers, which is a fair assumption because our constructor is only accepting natural numbers. And if statements say that if the condition is a natural number, and if both the true and the false blocks are of type T, then evaluating this thing over here will give you something of type T. This is basically saying if 0, then return this, but if this is non-zero, return this. Although I haven't actually defined the semantics like the way that this language runs, so that's not really relevant, I guess. But right, so this is cool because now we have a mechanism for checking whether expressions are well typed. Okay, and we do this by trying to construct proofs of well typedness from these things over here. Like for example, let's look at these two things again. So we want to show let's show that this expression over here, the identity function, is indeed well typed. Okay, so in Coq we would do that by saying lemma ID has type, which says that Oh, shoot. So just to make my own life easier, I'm going to make the argument annotated. Like I forgot to add the annotation for the argument over here. So I'm just gonna throw that over there and T1. So here we're saying that it's a lambda abstraction which takes something of type T1. And the reason this is important is because otherwise I can't really specify what this type is over here. So let's put T over there and T over here. And this goes from T to T. So for those of you who know Coq, what I'm going to do is fairly straightforward. For those of you who are not as familiar with Coq, so this is how you prove things in Coq essentially. So over here, I've specified a lemma that I wish to prove. And this lemma says that for any context G and any type T, the identity function, which accepts an argument of type T, is well typed as T to T. Okay. And indeed, I can prove this in Coq. So first I introduce all the variables into the context. So for those of you who are familiar with like the judgment form, this basically says that G is something that I have in, like I have a context G, I have a type T, and this is the final goal that I wish to prove. And I can try proving it by applying these things over here, which are the lemmas, which are basically, yeah, they're basically ways of constructing proofs. Okay, so the first thing I would do is I would try to apply this thing over here, because we have something of a form lam-t, like a lambda expression over here. And this rule over here tells us how to type lambda expressions. So if I try applying like tlam, it should say that like, okay, we have something like this in the conclusion of tlam. So as long as this holds, we can prove this, which is what will happen when I say apply tlam. And sure enough, something has happened over here. In particular, what's happened is it's asking me to prove this premise instead. So in Coq, like a lot of the proofs that you do in like hand, especially in the classes that we take in IIIT, we usually try proving things in a forward manner. But in Coq, typically things are proved backwards. Like we start at the conclusion and we say, yeah, this conclusion obviously holds if these premises hold, and so on and so forth. So with this, now we have a variable over here. So we want to probably use this rule over here, the tvar rule. So apply tvar. And now it's asking me to prove that this holds. Luckily, lookup is just a normal function in Coq, so I can ask Coq to just evaluate it like that, and it certainly gives me this. And when I have something where like I have the same expression on both sides of the equality, I can just prove this in Coq by using reflexivity. Okay, so by the way, these things over here, the ways in which we're manipulating the proof, these are called tactics. Okay, and they're like if you're familiar with Coq or Lean, you've definitely heard of this. If you're familiar with Agda, they've recently added this in the form of metaprogramming. But right, this is basically how you prove things in Coq. And now, like if Coq accepts the proof, assuming that you haven't made like axiomat, assuming you haven't asked Coq to accept something. If Coq says that a proof holds, then the proof holds given all the assumptions you've given Coq. Essentially, you can be sure that the proof holds. Okay. So right. So with this, we have proven indeed that the identity function is well typed. Okay. We should like, however, we will not be able to prove that like this function, which like makes no sense, is well typed, assuming that there was some t over here. Because 2 here is out of scope. So if we were to like, let's see what happens when we actually just try to prove it, just for kicks, like fail GPT. It says for all GPT, let's type G $2. Oh, damn it. I guess it's fine to make this a prop for now. So let's try proving it. Okay, so like clearly we're not going to be able to prove this. Okay, but I want to try and show you guys at like what point the proof fails, just so that you guys have better intuition on how this is working. So again, as we did earlier, we introduce a bunch of things into the we introduce everything into the premises. So because this is not really a well-typed term, I just said exists t dash such that this. So I need to find a particular t dash which works for this, but we know that this doesn't actually work. So I'm just going to fill this in with like nonsense. I'll fill this in with this, and we'll try to prove it. So we apply the t lam rule because again we have a lambda expression over here. And now we apply the t-var rule because we have a variable in the conclusion, t-var. Okay, and here we say simple. And we just get stuck over there. So it can't unfold G anymore because we don't have any information about whether G is nil or not. We could, excuse me, we could do a case analysis on G and like try in each case, but that won't yield any results either, because like, let's talk about the first case. We can simplify this further, and we just, now Coq asks us to prove that none is equal to some t, which is just false. Okay, so clearly this, like, Coq does not accept any invalid proof in this regard. And therefore we can be sure that our typing rules are indeed like, well, yeah, I hope that the point has been conveyed. Like, only terms which we specify will be well typed in this manner will be accepted. But if we, like, we can only prove the well typedness of well typed terms. Right. So this is.
I have a question.
Go ahead.
So like if you choose the context to be the list containing TTT,
Okay.
won't it succeed? Because lam #2 will like try to look up the element at index 2.
Yeah. So if I had changed this to say like instead of a for all exists G, then I could, yes, definitely. Then over here, I'm saying that there exists a certain G such that this is well typed, and that definitely holds. Yes. Okay. So yeah, that's actually a good point. So let's quickly run through this, and then I'll explain why it holds despite the fact that that expression doesn't really look well typed. So we introduce this into context, and here we say exists. What would work here again? T
T dash.
dash. Oh, we don't have a T dash yet. So let's. Switch these around. Sorry, I couldn't hear that very well.
No, that.
Right. So first exists. So let's just assume that T dash is just T, and exists T nil. So under this, we should definitely be able to prove this. So we go apply tlam. What's going on here? It says that unable to unify. Oh, the type over here is wrong. So this should not be T, but it should be, I guess, T to T. And here we just apply tvar simple reflexivity. So certainly this one works, where we fill in like the type and the context appropriately, but it doesn't hold for every context. And when we're talking about well-typed terms in the language, so our well-typedness criterion depends on the context. But if this was an actual programming language, which you were using to like code something out, then the implicit assumption is that your context starts off empty. And as you enter function bodies and stuff, you start filling up your context. But basically, so basically this holds. So I guess I should have not shown that. I guess it would have been more revealing if I showed that this holds under the empty context, because that's what we actually want to know. We want to know which terms are well typed under the empty context, because those are the meaningful terms. And of course, these things will slowly fill up the context as it goes inside functions. I hope that was clear. But yeah, so essentially, yes, this does work if you existentially quantify over the context, but it doesn't hold for every context. Whereas this up here actually does hold for every context.
Nitin, I think you can skip the details of Coq and everything, and yeah, just go into the like.
Cool. I'll do that from here on.
Yeah.
Okay. So this style of embedding a language where you first specify the syntactic terms and after the fact specify the typing rules. This is called extrinsic types, and typically we call these over here the preterms, because we don't and we reserve the word term for something which is actually well typed. So this gives us a little flexibility in the sense that like we can construct a lot more than just like well-typed terms, but you don't always need that. And like it also makes your proofs really big. Like when you're trying to prove interesting properties about the language, you need to prove it on like these predicates, which are different from this. It makes your system unnecessarily big and makes it difficult to prove things. So you typically want to keep it nice and concise. So because of that, people came up with something known as intrinsic style embeddings. And in intrinsic style embeddings, we define the terms, but in the definition of the terms, we specify the same premises that we actually have up here. Okay, so this is in fact the same language that we have over here, but specified intrinsically. So again, we have types, which are just natural numbers and like function types. Your context is just a list of types again. And these are intrinsically scoped variables. So variables here are indexed by the context and their type, okay? And there are two rules for constructing variables. There's the variable at position 0. So these are, again, de Bruijn indices, by the way. So this is the variable at position 0, which says that for any context and type, if you can get the variable at position 0 in this way. So, and this variable at position 0 is of type T. So this is a variable which is well typed as T under the context T cons G. And over here, this is the variable. This is kind of a successor function. So if I were to write, for example, I don't have a context, but maybe check SZ. So this is a well-formed variable, and SZ represents the variable at position 1. S of Z represents the variable at position 2, and so on and so forth. And we can see this from the type signature, which says that if we have a proof, if we have a variable which is well typed as T under G, then that variable is also well typed as T under this extended context. Yeah. I was just double checking and making sure that my definition is right. Yeah. So, right. So this was our first look at some intrinsic syntax, and it's very nice because now we don't have separate proofs for these properties. Like, in order to construct, let's talk about the terms before I get to that. So terms are also indexed by context and type. Okay, so we say that a variable is well typed at position T if we can construct it, because our construction only allows us to choose variables which are within context. If you notice above here, to say that a variable is not within the context, we just return none. But over here, it's a lot cleaner because we actually just can't construct a variable which is like under the empty context because we don't have a rule for it. Right. So if the variable is well typed as T under context G, then it is also a term well typed at T under context G. Lambda abstractions, the rule for lambda abstraction says that if you have the body, which is of this type, which basically means that under this extended context, it returns something of type T dash. This context is extended with the argument type. Then you can just take the body, wrap it in a lambda, and get something of this type. Okay, application is again the same as what we saw above, except in like this nice intrinsic syntax, numbers as well, and if statements as well. Okay, and sure enough, when we ask Coq if this will fail, Coq tells us yes, it will fail. Let me just first try to see if it succeeds, and it does not. So it says here that this term has like SZ needs to have at least 2 elements in the context. That's what this is trying to tell us. No, wait, give me a sec. Something's not right here. That's a weird error message. Yeah, I thought so. Oh, right, I made the same mistake. No, that's actually not it. What's going wrong here? Give me a quick sec, guys. Right, it actually expects the context, which is I forget the order of arguments which Coq needs for this.
You need the context for each thing, right?
Yeah, and I guess maybe it would help if I just put this in this. Yeah, and also the same thing over here. I forget, is this valid Coq syntax? Like
No, I don't think that works.
for all. This should work. Ah, what a pain.
No, you can't return that, right? You have to return a for all t type.
That was careless of me. I should have caught that before. And that, nice. Okay, so here we can check that the identity function like is indeed well typed. Like it's something that we can construct, and it's also well typed because we've already specified all like the requirements in the type signature itself. Okay, but similarly, I can't do the same thing for something which would not make sense, like this, where we're trying to refer to a variable which is out of scope. And what? Oh, because it's implicitly assuming that I have a larger context here. So if I were to actually specify the context in this fashion, and t to be, I don't know, n. No, it would have to be, I don't know, n to n. Why on earth does it expect? Oh, gotta fill in those as well. N. And is that the error message that I was hoping for? Yes, this is finally the error message I was hoping for. I'm so sorry about all the syntactic bullshit. I should have caught that beforehand. But essentially, you can kind of ignore these. These are like, so basically we're saying that the context is empty. Under the empty context, we cannot construct this lambda abstraction over here. And the reason for this is because, well, we expect that this term has this type. So n to n is the, let me actually make this n, because now I understand which ones it's unable to infer. So this is a function which we're trying to claim that this is a function which accepts a natural number and returns a natural number under the empty context. Okay, but it immediately points out that this variable is only well typed under a context which has n, which is like your argument, as well as this another thing over here, this t, because sz points directly at this variable. Okay, and then the rest of the context, which could be nil or whatever else. Okay, but in fact, it's expected to have this type over here, which is a much smaller context with just n, which is just false, and like we can't show this. And like therefore, in intrinsic syntax, you can only construct well-typed terms by construction. And Coq actually doesn't let you go any further with this. Like, I mean, it doesn't allow you to construct ill-typed terms, which is really nice. And makes our proofs really simple. Like, as a very trivial example, if I were to like define some operational semantics on this, which basically they're basically rules which describe how your program evaluates step by step. Then from every step, I would be able to show that in every step the type is preserved. And from this, we just get an automatic proof of preservation without even having to separately prove it as a lemma, which is really nice. Okay, but unfortunately, the intrinsically typed game does not work very well when we try talking about, when we try extending this to dependent types. So in a dependently typed language, you can have variables in your types. your types can refer to, like, your types are dependent on values as well as just like the normal types. And let me just pull up the relevant paper. I have it somewhere here. Outrageous. Right. So this is a very, very interesting paper by Conor McBride, where he starts off by just talking about the difficulties of extending this general method that we just saw to dependent types. Okay, we're not going to go through this paper in a lot of detail because it's pretty dense, but I do want to run through the introduction because it well motivates like the fact that it's difficult to have like intrinsic syntax in a dependently typed language. Okay, so he starts off by doing like he starts off in a very similar fashion to what we did. First, he shows it for like a non-dependently typed language. So this is Agda, by the way. These declarations over here are equivalent to inductive in Coq. So and like when we have something like underscore something underscore, that's basically like this is an infix operator, which takes like an argument on the left and the right side. So here he constructs the type of types in our language, which he calls star. This is a base type, and this is a function type. Okay, and contexts are simply either the empty context or a context extended with a type, which is pretty much just a list, like just like we saw in our encodings. And variables are defined in pretty much the exact way that I showed you over there, except that because this is Agda and like because he's the syntax is a lot nicer than what I did. But yeah. So this is my zero constructor, like what I did with Z. It says that like it refers to the variable, like the outermost variable in the context. And pop is like the successor thing that I was talking about, which says that if something is well typed as T under gamma, then it's definitely well typed as T under an extended gamma. And our terms in our language are also intrinsically scoped in the exact same way that we saw. Like, yeah, I don't think there's anything in particular that's very interesting in this. Okay. And right. And from this, you can just directly define an interpretation function, which maps our deep embeddings to shallow embeddings in Agda. Okay. For example, they interpret the base type as natural numbers, and they interpret function types as function types. They interpret the empty context as this is not actually one. This is a unit type, like a type which has a single element. And like the extended context is just a tuple. And your top pulls out the last thing in the environment, and your successor recursively calls itself on the arguments. These are fairly straightforward. I don't want to dwell too much on this, but the point is the formula which we just laid out is well understood and it makes sense. But when we try extending this to dependent types, it gets tricky. And the reason is dependent types can have variables in them, which means that not all the type, like just like how in extrinsic syntax we had preterms which are not necessarily well typed, in dependent types we have pretypes which are not necessarily well typed. You need to define types, you need to define a well-formedness condition for types which is dependent on your context. Okay, and here McBride makes an attempt at doing that. So first of all, the fact that your types are now dependent on your contexts and the fact that you can have variables in your types means that all these definitions up here get entangled. Like now we have to define them mutually, which can be very annoying when you have to prove things about these things later. So this is the way that AGDA used to do mutual definition. Now it does it in a lot cleaner way, although I believe that this deprecated syntax still works. So these are 3 data types which are mutually defined. Okay, so this is the type of the context, the type of the type, and the type of the terms. Okay, this is the TM that I was defining in the in like my syntax. Right. So unfortunately, this attempt actually doesn't work out, and he will explain why. But let's just quickly try and see what he's doing here, just so that we understand it a little better. Okay. So first note, the first difference that we should note is in the extended context. So over here, the extended context is like literally just extending your context with a type. This is literally just a list. Okay. But it's different over here. Here we have, like, the first argument is indeed a context, but the second argument is a type which is indexed by the context. In other words, whenever you add a type to the context, that type is dependent on everything that previously existed in the context. Okay? And why is it dependent on everything that previously existed in the context? Because your type might contain a variable. And this variable, well, in order to understand like whether this type is well formed, this variable needs to exist in the context at the very least, and maybe a few more things depending on how rich your language is. Okay, so the literature calls this, like, we say that a variable is in scope if it's in the context, and by, like, I don't know, someone thought they were being cute, and they say that, like, over here you can see that every type is dependent on everything previous in the context. They call that a telescope. Okay, so yeah, suddenly our contexts are a lot more complicated. Let's look at the types. So this is a pi type. So pi types are just function types, but the difference is that the return type may be dependent on the function argument. Okay, so an example of a dependent function type would be, for example, say a function which takes a natural number and returns a list with, like, let's assume it takes a natural number n, and it returns a list with n zeros. Like, you could visualize this as an example of a dependent function type, because the return type is or maybe a vector is a better terminology in this case. Like, the return type is a vector with n zeros, and this is specified in the type. Right. So pi types are of this form over here, and this says that it takes, this is the type of the argument, which is tie gamma. Like, it's a type which is well formed under gamma, and the return type is well formed under gamma extended with the argument. And if we have both of these, then we get a function type which is well typed under gamma. Yeah, similarly, he also defines Boolean types, which he calls 2 because there are only 2 elements in it. And like if statements, like this is if on a type level. It basically says that if this is true, then this type, else this type. And please notice that, like, both these types are well typed under gamma. So this weird syntax is the syntax that we see over here for defining expressions, well typed terms in our language. Okay, this says that the term is well typed under context gamma as a Boolean. Okay, and like, let's just run through these rules. So the lambda rule is pretty much the same thing that we saw earlier, which is to say that if you have an expression which is well typed as T under this extended context, then wrapping that in a lambda with an argument of type S will just give you a function of type pi st or s to t. Okay, this pi type is pretty much the same thing as the for all type in Coq, by the way, just to be clear. Okay, and application is again defined in a rather intuitive manner, which says that if you have a function from S to T and an argument of S, they made a mistake here, this should be gamma, an argument of type S, then the return type is T with S applied to it. So if you remember, T is like this thing which lives inside gamma comma S. So this application thing basically like it informs T what that S is. And like it's not very well defined here. But the reason it's not very well defined is because there's actually like, if you were to proceed in this manner and try to embed your dependently typed language, it's actually not clear how to represent this. There are several choices and like no real clear winner in this particular form of embedding. Okay, and we'll talk about that soon. And then we have true and false. So I hope that I provided an intuition for what McBride attempted to do here. And now now we're gonna explain why this approach, like despite going through such lengths, still does not work out. And like, basically what are the questions that still arise? What is wrong with this approach? Okay, like the first thing like that you should notice is like, first of all, he hasn't defined variables yet. Okay, he's like hidden the definition away. And the reason for this is because if you were to try to define variables in the same way, this is actually not well typed. Okay, let's look very carefully at this type signature. Okay, this, so gamma in S is how we represent, gamma contains S is how we represent a variable which is well typed as S under a context gamma. Okay, so first we tried defining the top in the same way that we did above, but in fact, this T needs to be this T needs to be dependent on this context over here. Okay, so the fact that we put T, the fact that we can construct gamma comma T by our constructor over here tells us that T must be of type tie gamma, clearly from this constructor. Okay, however, T is also dependent on this, and we also need to show that T is of type tie gamma comma T, which is just not true here. Like, we need to find a way to basically weaken the type of T. Like, we know that T, from the fact that we can even construct this, we know that T is well typed as tie gamma. Okay, we need to show that if something is well typed as tie gamma, it is obviously also well typed at tie gamma comma S. And it's just not immediately clear how to do that from here. Like, if we were to define it in this particular way. And like, a couple of other things is that like the application rule, like there are lots of choices that you can make. Like you could probably define some semantic function which does it, which applies it, but it's not clear how you would do that immediately. Another thing you could do is you could add this form as an extra syntactic form in the language, which would allow you to definitely reason about things in like a decent manner, but it's really fucking ugly. Like, suddenly you have an extra syntactic form in your language, which you have to reason about in all the proofs. It's not nice. And most importantly, however, like, so if you notice the name of the paper, it was called Outrageous but Meaningful Coincidences. And the reason it's called that is because the application constructor demands that this type and this type coincide. The argument type and the type of, well, the argument coincide, which makes sense. Okay, but in our language, we have these two types, for example. Excuse me. If true, Boolean, Boolean, and just Boolean. Now, clearly, these two types are the same thing. Like, they should be compatible. They ought to be identified as the same thing. Okay, but but they are syntactically different constructors, and therefore, like, without giving Coq any more information, it 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 can't figure that out. Okay, and in order to get around this, you need to define a whole new set of rules, which defines equality of two syntactic types under a context gamma. And once you define these rules, then you need to add another form to the terms, which allows you to explicitly cast something. So if you have an expression of type S and a proof that S is equivalent to T, then we can cast that expression to type T. That's basically the intuition behind this. But right, so essentially extending these techniques, like extending particularly intrinsic type, like intrinsic style of embedding a language, extend this to dependent type, like dependently typed languages, is actually pretty tough and like quite complicated, like, which is why, like, almost every time you have an interesting calculus and someone comes up with intrinsic types, that's usually worth the paper. McBride does a lot of work in this area, and like his work is beautiful. His right. So, how much more time do I have?
I mean,
yeah. Right. I think I'm going to conclude at this point. I did hope to get a bit more done, but right. Does anyone have any particular questions or maybe a direction that like you'd like to explore later?
I mean, can you say
Okay.
a couple of sentences about what happens in the paper at the end? Like, yeah.
Okay, so yeah, this paper is honestly sick. So, so he starts by constructing shallow embeddings for language. Like, let's just quickly run through the sections. So the language which he's talking about, has he written the syntax anywhere? Oh, that's annoying. Okay, so the language which he's talking about contains like the zero type, which is basically the type with no with no inhabitants. One, which is the type with exactly one inhabitant, and two, which is booleans, as well as natural numbers. Okay, and he also has sigma types and pi type, whatever. He has a bunch of different types. And first he constructs shallow embeddings for this language. So here he, like, for example, here's the zero type, and it has no inhabitants, which is why you just say where, and that's it, you're done. And magic is just a function which takes anything of the zero type and returns pretty much anything. And the reason this is valid is because there are no inhabitants of the zero type. So if, like, this is equivalent to like false in Coq, for those who are familiar with that. Like, basically, if you have, like, false also has no inhabitants. And the idea is that, like, if you can construct an inhabitant of this, which is supposed to be impossible, then you can do anything you like because you've already proved false is true. So here he constructs like shallow embeddings of the language. And from those shallow embeddings, like, he then defines a universe of types in this form. So this over here is a particular, it's a cute feature of Agda called induction recursion, where you inductively define a data type mutually recursive, like mutually with a recursive function. Okay, so like, for example, and the idea of using induction recursive to encode a universe of types is that you can like define U, which is like a type code, and L, which is a function which takes the type code and returns a type in Agda. So for example, the type code for pi types, it takes another type code and something which takes an element of this type code to another type code, which is basically representing your dependence, like the second type is dependent on the first type, and returns another type code. And when we decode this, it just translates directly to a function in Agda, a function type in Agda. Okay, so using induction recursion, he constructs this universe of types. He does the same, like he does similar things for, like he uses induction recursion to do the same thing for contexts, as well as variables. So the fact that like, so contexts are interpreted as dependent tuples. This sigma here represents sigma types in Agda, which is basically just the type of a dependent tuple. And right, so the first element of this dependent tuple is basically the like interpretation of this context, and the like the extension is something which depends on this context. Okay, so here you can see that we've actually captured the telescope that we were talking about earlier. Like we've captured it semantically. Uh, and because we've captured it in the form of a dependent tuple, it allows us to do this really neat thing where we can implement weakening by just taking the first projection of this type. So this type is something of type tie gamma, comma s. And if we just take the first projection of something of tie gamma s, we get something of type tie gamma, which is like awesome and like really cute. But I mean, it's a good technique, but it's not. Well, I guess this is extensible for variables at least, but how useful it is a question. Right. Here he defines a bunch of combinators because McBride loves combinators because he thinks it makes things more readable, which is definitely true, but it also makes it harder to grok things in my opinion, which I dislike. And then using these combinators and these inductive recursive definitions, he actually constructs something that looks like deep embeddings. Okay, like, so yes, this is your type formation rule, which says that so yeah, so he uses this thing known as a gamma type. So if you remember, like where like every type needs to be dependent on every previous type in the context. So this is what he uses to capture that idea. Something which takes a context and returns the type code. And so, right, like for example, he can construct the type formation rule for 0 by saying that under any context gamma, the type code for 0 lifted to a function is well formed. This K combinator thing is basically something which takes the body and like it turns this into a function which just discards its argument. And like he goes and he does some fancy stuff and constructs like a proper deep embedding using these combinators. Yeah, it's very pretty, but as I quickly learned when I attempted to apply this to my current research, it doesn't really extend very nicely, not to all languages at least. Or maybe that's just because Dot is weird, I'm not sure. But right, so after that, he actually goes one step further though, and he creates something which allows you to actually like use these like well-formed type constructors to as normal type signatures in Agda. This brackets thing interprets this deep like these well-formed types as Agda types. And since our terms like and our terms, yeah, our terms are also interpreted into Agda types. So this is actually really pretty, but again, it doesn't work for all languages, which is really frustrating. And he goes further to show that like you can actually like get an like in his simple language just has if statements. Oh yeah, it has if statements. That's why he calls this language Kipling, because if by Rudyard Kipling. Yeah, whatever. So here is like he proves like equality, and like this is like the type of for this is a proof of reflexivity. It's so he's like he mentioned that this does not type check, but it should. I don't really remember what that note was about. Right. And after this, like, so clearly he's jumped through some hoops to get deep embeddings which look like the deep embeddings that we want, but like he's used all these weird combinators and stuff. So I claim to have implemented Kipling, but apparently I am lying. So essentially it doesn't work as cutely as he wants it to, like because of this thing over here. And I don't really remember what was wrong with this, so I'm not going to talk about that. But and here he like does some basic formal stuff where he tries mapping syntactic terms to like things into this thing and tries to figure out what exactly goes wrong and yada yada yada. It gets very detailed here, very deep. But yeah, the overall idea was that he created shallow embeddings. From those shallow embeddings, he constructed a universe of types via reduction recursion. From that universe of types, he constructed deep embeddings, which looked really, really nice, but didn't play as nicely as he hoped. However, this was a very big step in the right direction. And I believe there is further work which does things in a quote unquote nicer way. And by nicer, I mean more extensible to other languages. But nonetheless, this is this work is a piece of art, in my opinion. It's fucking beautiful. Useful, maybe not, but beautiful. Yeah, that's basically the idea behind this work. Oh yeah, he also talks about how to extend that previous language with a universe of types itself. Like whatever, yeah. We can talk about it offline. Okay, and thanks everyone. Like, this was fun.
Thank you very much for the talk.
Thank you.